All right, let's get it done. Make sure you have a graphing calculator because, well, solving logarithms, it's pretty darn useful. Okay, so we talked about solving values within an exponential growth function. And anytime, well, not anytime, pretty much anytime you have to solve for an exponent, if your variable is an exponent, most of the time you're going to end up needing to use a logarithm in order to solve that. That's what makes them super useful in a lot of cases with algebra. So we talked about exponential growth, and then we started in with an exponential decay, and it's the exact same formula. The only difference, if you remember, is growth has a k value. Decay also has a k value. However, there is a negative in front of the k value here. And I also want to remind you that k is positive in both the growth and decay functions. It's just that there is a negative in front of k. So it's the opposite of whatever k is, even though k is positive. K will always be a positive number. Growth, we don't make it opposite. Decay, we do make it opposite. So that's the big difference there. All right, let's head on back. We were talking about this thing called thorium 230. I don't know what that means, but we're talking about it. And we're figuring out the value of k, which is the decay rate. And we got to ln of 0.5 divided by negative 75,381. What's that? We are an 8.5. All right, so then we're going to divide each side. You're going to take ln, so not log, math fraction, ln of 0.5. And we're going to divide that by negative 75,381. And before we get an answer here, let's just do a quick recap. We're talking about a half-life. And so remember, a half-life just means that whatever you start with, you're going to end with half of that thing. So if you have an A value for your initial amount, then the remaining value will be half of that. And even though there's two variables to begin with, in order to isolate the power, we had to divide both sides by A, which got rid of A. So we're going to end up with only one variable to solve for, and that's the variable that is up in our exponent. So enter. That's kind of a nasty number. Now I'm trying to think here. If I can get this to, it's not going to let me. This is giving our answer in scientific notation. When you have that E, like capital E, not lowercase e, capital E does not mean about 2.7181, whatever it is. Capital E means times 10 to the power of, and then negative 6. So what this means here is, we're just going to say, we can write this off the side, 9.195. I'm just going to stop there, times 10 to the negative 6th power. That's what that means. And so that is equal to 9.195 e negative 6. So your calculator will write scientific notation like this. And we generally write scientific notation like this. So if you want to, you could type in 9.915 times 10 and then raise that to the negative 6, and hopefully, shoot, it didn't do it. It kept it in the scientific notation. It was worth a try. So really all we need to do, because it says negative 6 for the exponent, we're going to move our decimal 6 spaces to the left because it needs to get it smaller. And then we're going to fill in the gaps with zeros. So really what's going to end up happening is this is going to be there's going to be 5 zeros. 1, 2, 3, 4, 5, and then 9,195. And then you can see over here, it is 1, 2, 3, 4, 5. And they rounded the 9,195 to 92. So anytime you have anytime you have scientific notation and you have a negative exponent, you're going to move your decimal that many spaces to the left. If it's a positive exponent, you'd move it that many spaces to the right. Question? Oh, no. Okay. And then we're looking for a rate here. So this is the decimal value. So if we want the percentage, that means we're going to have to multiply this by 100 or just move the decimal places back to the right. I guess that would be right for you. Back to the right a couple spaces. That'll be there. So the rate is 0.00092% per year. So it's decaying very, very, very slowly, which makes sense because if you think about what the half-life was, it was 75,381 years, which means if it takes that long for half of the material to remain, that takes a really long time, which means it has to be decaying really, really, really slowly. So our K value is going to be 0.1234592. So 5 zeros and a 92, which means the equation that we're going to use is here. That's our equation. Because remember, when we write our equation, we don't have a value of an initial value or a current value. But what we do have is y equals whatever that initial value is going to be times e to the k value, which we do need. And then t is our x coordinate. So that's what it's going to be. That's our generic formula there. Now, the question says, how much of a 2-gram sample should be left after 1,500 years? So honestly, most of it is going to be left because we're talking about 1,500 years. How long does it take for it to reach half of the original amount? Based on part A? Yeah, it takes that long for it to reach half of the original amount. So it's going to take this long for it to go from 2 grams to 1 gram. So in terms of 1,500 years, that's just a fraction of 75,381 years. So there should be a whole lot of this left. And this one actually doesn't involve any algebra whatsoever. We can just type this directly into our calculators because the initial amount here is what? 2. So the initial amount, lowercase a, is 2. And then this is our time here, which means if we have a value for a and we have a value for t, we're solving for y, which means we just have to plug that in and solve. And so let's see, a, we already have our a value, it's 2. A is 2, t is 1,500. And then you can type it in. They've already done the work for us, but 1.97. So the vast majority of the material is still left. So after 1,500 years, there will be about 1.97 grams of thorium-230 remaining. So since thorium-230 has such a long half-life, it is reasonable that over 1,500 years, only a small amount, 0.03 grams, of the original sample would have decayed, which is kind of what I was mentioning before. This makes good sense. All right, let's do a check one. Iodine-131, a radioactive isotope commonly used to treat thyroid cancer, has a half-life of 8.02 days. Oh, dang. That's not a very long time. Generally speaking, so if you're, anybody here familiar with half-lives? Like in terms of radioactivity-ish? So the shorter the half-life, the more radioactive it is. Because what it means is it's emitting, if it's losing half of its radioactivity in 8 days, that means it's releasing a lot of it within 8 days, which means it's highly radioactive. Versus this one, taking that long to reach half, it's only emitting a tiny little bit of radioactive material. So, which one? Thorium? For sites? Is it a gas? Yeah.
It's a type of metal. I want to call it metal, but it's a thing that's used on like military kind of site.
Okay, so it's used as like the surround.
Yeah.
Okay. Got it. So if you, I mean, most materials have some amount of radioactivity, but most of them have such low levels that they're not dangerous. And so that right there, I would assume, I'm not a scientist, so I don't actually know, so don't quote me on this, but I would assume that this is not dangerous. If it takes that long for half of it to be left in terms of the material, that doesn't seem dangerous to me. This, however, seems pretty dangerous. So this is to be used only in, you know, highly controlled environments. And if it's used to treat thyroid cancer, if you've ever heard of like, you know, different types of treatments that you can get for different types of cancers, some of them use radiation, and this is one of them. And so the radiation, like it actually attacks your body, but it's designed to attack the part of your body that shouldn't be there, i.e. the cancer. So write the continuous exponential decay equation for iodine-131. round the value of k to the nearest 10,000. So we're going 4 decimal places. So let's go ahead and take a look. We are going to say, we don't know how much we're starting with. We don't know how much we're ending with, but we're talking about a half-life. So we are ending with half of what we started with. So we're going to write 0.5a is equal to a times e to the number of days is 8.02. And we're talking about k is what we're trying to figure out. Now, what am I missing here? Because we're talking about decay, something is missing from my equation. The negative, yeah. We have to take the opposite of that exponent because it has to decrease instead of increase. That's the main key for the decay factor, is that the decay factor itself is not negative, but the exponent needs to be negative. So that is important when we're talking about decay. All right, so then what do we do to isolate our power over here? We have to get e to the negative 8.02k by itself. Divide by a. So we'll divide each side by a. A's cancel out on both sides, which gives us 0.5 equals e to the negative 8.02k. Now, if we're trying to solve for something in a variable in an exponent with a base of e, it's going to be most convenient for us to use what? ln, yeah, apply ln to both sides. ln e is 1, so that's going to cancel. And we're going to have ln 0.5 equals negative 8.02k. Anytime you are dealing with a half-life, you will always end up with ln 0.5 over here because it's always going to be half of what you started with. 0.5 would be half. And then we'll divide both sides by negative 8.02, and k is going to equal ln 0.5 divided by negative 8.02, which will be approximately, let's find out. Oh, good. This one was not in scientific notation, so we can go with 4 decimal places, 0.086, looks like 4. So the decay rate, if we move this back to the right a couple of spaces, is going to be about 8.64%. However, we don't need to worry about that. That's not something we need to write. We just need to write the equation. So now that we have k, we're going to plug that back into our equation and say y is equal to a, because again, this is a generic equation, so we're going to assume we don't know how much we're starting with or how much we're ending with. So the start value we don't know, the end value we don't know, but we know we're going to have e to the negative 0.0864, and then whatever t is, we can use that as well. So there you go. All right. Now we can go ahead and say how much is left after 20 days if we start with a 15-gram sample. So this is going to be y, because we don't know the end value, but we know the start value a is 15, times e to the negative 0.0864 times our t value, which is 20 for 20 days. Now I would imagine there's not going to be a whole lot left because the decay rate is pretty darn quick. But let's figure it out. I would say there's going to be less than a quarter of the original amount left that would be my assumption. So less than 3.75. Let's see. 15 e to the negative 0.0864 times 20. Yeah, less than 3.75. So about, round to the nearest 10th, about 2.7. Cool. And the reason why I was able to kind of estimate that in my mind is because it takes almost exactly 8 days to reduce the original amount by half. So half of 15 would be 7.5. And then another 8 days pass, so we're at 16 days, and we're going for 20 days total. So half of 7.5 would be 3.75. And then there's another 4 days after that still, roughly. And so, yeah, we're looking at less than a quarter of the original, about 2.7. Okay, last problem. Let's do this. Archaeology. All right, we talked about carbon-14 back in, actually, Bryce had that question yesterday about lesson 8.4, problem number 55, that talked about carbon-14. This example here, carbon-14, is used to date the objects in a method called radiocarbon dating. Radio meaning the radioactivity of the material over time. Carbon-14 has a half-life of 5,730 years and a decay constant K of 0.00012. So we have our K value. In 2016, charcoal flakes from the excavation site in an ancient human settlement in Canada were sent for radiocarbon dating. If the charcoal flakes were found to contain about 18.6% as much carbon as they would have originally contained, how old are the charcoal flakes to the nearest year? Okay. Describe the task in your own words. Basically, what are we trying to figure out? Yeah. So find out how old the carbon flakes are. Cool. Now the question is, how will you approach the task? Is this going to be exponential growth or exponential decay? Is the amount of carbon increasing or decreasing over time? It's decreasing, yeah, because we're talking about half-life. Half-life means it's going down over time. So that means we are going to use y equals a times e to the negative kt in order to solve. So let's go ahead and write out what we know. We're talking about a half-life. So if the original value is a, we don't know how much they started with, right? The original amount we don't know. So original amount is, we'll just call it A. The current amount, though, is not half of the original. How much is left? (18.6% remains of the original. So 18.6% of A, which equals 0.186A. That is our Y value. Any questions about how we got that? Current amount is always Y, and because we don't know exactly how much there is, but we have a relationship between the two, we're going to divide by A like we've been doing, so the A's are going to go away. And then what is our K value? It just told it to us. Yeah, 0.00012, so 3 zeros after the decimal and a 1, 2. And what's our T value? So that's definitely our half-life, right? Okay. However, we're not ending up with exactly half of what we started with, right? So our T value might not be, it might be, but it might not be. So let's think about that for a second. Could it be that, or might it be something else? We don't really know. Time T means how long it takes, right? So if we were to write an equation for the half-life, we would say 0.5 equals, well, we'd say 0.5 equals A times e to the negative 0.00012 times 5,730. But that means we would have everything there and we wouldn't need to do anything with it. So we're trying to figure out not how much, like how long it took to get to 50%. We're trying to figure out how long it took to get to 18.6%. But because we have the decay rate, that means we don't really need to worry about t. That's what we're solving for. So solve for t. So the equation that we're going to use to solve is 0.186a equals a times e to the negative, don't forget your negative because that's always part of the decay equation, 0.123, 3 zeros and a 1, 2, and then t. That's our equation that we're solving right there. And whatever t is tells us how long it took for that to happen. So let's keep going. Let's solve this thing. I'm just going to move it up here. Now, the first thing we would do to get the power by itself is what? Yeah. We would divide by a on both sides, which would give us, I'm just going to write the result of that, 0.186 equals, the a cancels out, so e to the negative 0.00012 t. All right, now what? Variables in the exponent. So, yeah, ln, because we got to use the, well, we don't have to use the natural log, but it's definitely the quickest way to solve this. Ln e cancels out on the right, so we're going to have ln of 0.186 equals negative 0.00012 t. And then we divide both sides by the negative 0.00012, and so t is going to equal ln of 0.186 divided by negative 0.00012. So t is approximately, get that typed in, math fraction ln 0.186 over negative 0.12312. And we're going to the nearest year. So if you round it to the nearest whole number, what do you get? $14,017, yeah. So t is approximately 14,017, which means down here at the bottom, our solution is about 14,017. That's our t value. What does that mean in the context of the situation? Okay, so the flakes were about how old? About how old were they? They were about 14,017 years old. In what year? When were they found? In 2016. Good. Sweet. Any questions on that? I'm guessing this was taken from an actual thing that happened in real life, which is great. It allows us to actually use the things that we need. All right, let's turn the page, and we're almost done. We just have a little bit more to go. How can you write an argument that can be used to defend your solution? Well, honestly, you could graph it on a graphing calculator. You don't need to write that, but you could certainly do that. So let's take a look here. Very last one. An archaeologist examining a prehistoric painting examines that estimates that it contains about 2.34% as much carbon-14 as it would have contained when it was painted. How long ago was the painting created? Round to the nearest year. And remember, we already have the formula. That's great. So let's just go ahead and say initial amount is A. And the current amount is what? What's the current amount? How much is left? Okay, so what would that be in terms of A? Question? Yeah. So we've got our Y value here. We have our A value here. So let's just go ahead and drop those two things into this equation. And then it becomes the exact same thing as what we just did on the last page, which is great. Same formula. We're just plugging in different values for Y and A than we did on the previous page. The negative 0.00012 is still the same thing. So we've got ourselves 0.0234A question mark equals A to the E, A times E to the negative 0.00012 times T. And once again, we're solving for T. So I'd like you to solve for T real quick and then estimate how long ago the painting was made. Prehistoric, I'm guessing it was in a cave. So we'll call it a cave painting because that's a thing. Take a minute or two on that and we'll see how that ends up. I don't even have it for today. 55, is that right? Ooh, only 12 minutes in. Holy cow. Anybody have a number? What'd you get? I'll do that, but I'll raise you one. Cool. All right, so 31,000, about 31,292. That's old. The rounding, yeah. It's still before, it's morning still, we're fine. All right, that's all I got for you. That's it for the unit 1 through 17 odds is going to be your assignment. That'll be due on Monday.